Well, what we have done so far is to build a model for the crack growth rate. And we've systematically improved this model starting from a very basic proposal, a proposal that certainly worked in some way, but we've generalized it further to incorporate the influence of the stress range, the absolute actually value of the stress intensity factor in the high range even, and the range of the stress in particular. So we are able to predict the crack growth rate quite well. But remember what our goal was to begin with. You give me a certain structure and it has a certain crack in it, or I know that there is a crack of size, minimum detectable crack size within the structure, so I cannot see it, I cannot detect it, but I have to assume it's there. And I am interested in the number of cycles to failure. I want to predict it, because if I can, then to within a safety factor, I will know when to service this life when it is subjected to a cyclic loading. So that's my goal, to predict the number of cycles that it takes for the crack to grow from one value to another. So now let us make use of our model for that purpose. This is called, therefore, a life estimate. And remember, we're doing this for constant amplitude loading. If it is a variable amplitude loading, we can certainly do something as well. It's just going to be a little bit more complicated. So in general, this is what we have. Okay, and therefore now let me do the following. First, what I will do is I will write this equation in the reverse fashion. So I will write dn goes to the right, f comes below dA, so dA divided by f delta k r. Okay, and therefore what I can do is I can integrate both sides and my purpose will ultimately be the following. Now, this is the number of cycles. This is the crack size. I know that my model is going to predict a curve that is of this type. That's also the experimental observation. And the question is, well, how many cycles will it take for the crack to grow from one value to another? The number of cycles that I'm looking at can be the value that goes from the minimum detectable crack size all the way to the critical crack size at which ultimately fracture occurs. Or for that matter, it can be any initial value of the crack size towards any final value before failure. So the question is, how many cycles is it going to take? Well, the number of cycles it takes is precisely this distance. So I am at an initial number of cycles. This is the final number of cycles, and the number of cycles it is taking is nf minus ni, which we can also define as nif, number of cycles from some initial to final value. So that's the piece of information that we want, and that piece of information is actually here, right? We are trying to make a relation between the crack growth and the number of cycles. I now have a mathematical relation, and within that relation, the number of cycles goes from Ni to Nf, and the crack simultaneously grows from Ai to Af. So I just want to integrate both sides. So the left-hand side becomes integral Ni to Nf dn is simply nf minus ni, which is nif, number of cycles associated with that growth process. And on the right hand side we have, right, so this is now the equality that comes from our model, right? I know f because I have a model now, and that's the beauty of having a model. Now I can make use of that model, and I can integrate the crack size from AI to AF delta K R. Okay. So now, well, how do I carry out the integration? Now, in all cases, f, the function f, is of the form some constant. Now, I'm going to write here a constant as if it is the Paris equation, but we know that that is a constant, a parameter that depends on R if it's the Walker equation, and moreover, it also depends on the value of the stress intensity factor if it is the Forman equation. So it's not really a constant, it's just a parameter. Delta K to some power m. So this is true, this form is true for Paris, for Walker, which is its natural generalization, and it's their generalization to the high range, which is the Forman equation. So if I now go ahead and plug in the expression, at least keep in mind that C is not a constant. Let's just write C once again. I'll go ahead and plug in the expression for delta K. It is a form factor multiplying the stress range root pi A to a power m. So we can take that, plug that in there, and we can write that NIF is equal to integral AI AF dA divided by CF delta S root pi A to power m. Okay. So now let me isolate A from that integral. Okay, so I will write dA over A to the power m over 2. And then I'll put everything else as a factor within the integrand. The process that I am following will be greatly simplified if all of these are constants. That is certainly the case if I'm working with the Paris equation or the Walker equation with constant amplitude loading. In that case, the R that goes into this parameter C for Walker will not change over time as well. So in that case, C will also be a constant, F delta S root pi to power m. So this is a constant will come out of the integral. So for that particular case, you have to know and understand how to carry out this integration that we are doing presently. Okay, so keep that in mind. So since we know and understand the Paris equation, we can easily proceed through this idea and calculate NIF. But presently, what is the complication with this expression? Well, there are two complications. One, C is not a constant in general. Two, F is not a constant in general, so let us not also forget that F is actually a function of alpha, which is the ratio of the crack size to the stress, to the width of the, say, the plate, if we have a plate indeed. So as the crack grows, the value of F will change as well. So there are a lot of complications with this integration. Now, in general, for the Forman equation, the stress intensity also goes into C, so that certainly changes over time. If I have a computer, right, I can easily integrate this thing irrespective of whether I have Forman, whether I have variable amplitude, etc. And variable amplitude will just go in through the value, changing values of delta S, changing value of R, etc. Now, of course, another question, if we have variable amplitude, is to have reliable data that has been determined for variable amplitude. But conceptually, if the parameters that I have, if the forms of Walker, Forman, etc. are valid for that scenario, if the parameters are valid, then the integration theoretically is simple, but analytically it may be hard. Okay, so for analytical purposes, we are going to make some simplifications. So I am going to write here a big if. At least, again, remember, many things we do, many simplifications, in reality may not have to be done. But for the purposes of back-of-the-envelope calculations, quick solutions, these are certainly viable approaches. Okay, so if C, F, delta S, and M, everything that appears here are constant, then, right, I can simply take that factor outside of the integrand, and I can write NIF is equal to, alright, so first of all, my constant C is there, F delta S root pi to the power m is going to be there. So that's the factor that I've taken out of the integral. And then I will have here a to the power minus m over 2. I'm gonna add 1, so it will be a to the power 1 minus m over 2. And I'm gonna evaluate it at the final value and subtract the initial value from it. I've raised it to an exponent 1 minus m over 2, so I should also remember as I integrate to divide by 1 minus m over 2. So that is now our expression for the life. That's our life estimate. Clearly, I have assumed that m is not equal to 2, because if it's equal to 2, the integral would not be a power form, but it would be a logarithmic form. So m is not equal to 2. Okay, often this is true, but just for theoretical purposes, you may want to just do the same thing, that final step, for the case when m is actually equal to 2. Okay, so now this is our life estimate. And what it says is, if the crack grows from an initial value to a final value, or you want to determine how long it will take for it to grow from the initial to the final value, this is your estimate, to within the approximations that we are making, which we need to talk about a little bit more. Conversely, if you know the initial crack size, which might again be the minimum detectable crack size, and you know that this structure experiences a certain number of cycles, and you are wondering what the new size of the crack is, if you know this and that, then you can also determine that. So the life estimate is also going to, this equation is also going to let you determine the final value of a crack, should you know the initial value of the crack size and the number of cycles that the structure experiences. So it is an approximate form due to some assumptions that we have made, but still it is a form that will guide us in our back-of-the-envelope calculations. So next I will solve an example to demonstrate this idea, which essentially incorporates everything that we have discussed in the context of crack growth.